Welcome to the deep dive. Today we're tackling something pretty fundamental in software development, pointers.
hmm Can't get away from them, really.
Exactly. They're, how we manage memory, build all our data structures, and traditionally a pointer size is tied to your system's address space.
Right, like you need log n bits,
Yeah.
basically, to point anywhere in len locations.
Yeah, think of it like needing enough digits in a phone number to call anyone in the country. Simple enough. But what if we could use, like, much shorter numbers most of the time?
And that's where tiny pointers come in. That's the focus of our deep dive
So
today.
they're pointers.
Yeah, they're these novel data structural objects, and the idea is to use significantly fewer bits. Specifically, the goal is the goal of bits that's a little of log n.
Little o, okay. So substantially less than the standard login.
Way less in many applications. Just imagine the space savings if you could shrink every memory address in some huge application.
Okay, yeah, for us developers, that sounds like it could have a real impact. So why should we get excited about these? What's the practical upside?
Well, the big win is really reducing memory footprint. That's the main thing.
Right.
So if you're dealing with huge data sets, maybe in-memory databases or applications squeezed into tight memory budgets, shrinking pointers can mean really substantial overall memory savings.
Makes sense.
Think of it. If your app has millions, maybe billions of objects, and each one has several pointers, even shaving off a few bits per pointer adds up fast.
Oh, absolutely. That's potentially a lot of freed up RAM. Could boost performance, let you handle bigger workloads.
Exactly.
Right? Every byte counts, especially when you're working at scale. So today we're diving into the Tiny Pointers research paper. It's from ACM Transactions on Algorithms.
A solid source.
Yeah,
Yeah.
and we want to understand how this space-saving magic works and where we can actually use it. So we'll look at the core ideas, the optimal sizes, and maybe some surprising applications in data structures we use every day.
And there's a really interesting connection here, too,
Oh, yeah.
to some recent work by an undergraduate, Krapivin. He was exploring efficient data structures, kind of unaware of this 40-year-old conjecture by Yao about hash tables.
Wait, unaware of a 40-year-old famous conjecture?
Apparently.
Yeah.
And he stumbled onto ideas related to efficient data management, maybe touching on similar principles to tiny pointers, and ended up creating a new kind of hash table.
Wow.
Yeah, and this hash table actually outperformed what everyone thought was the theoretical limit for certain types of hash tables.
That's amazing. An undergrad rethinking something so fundamental.
It really is. It shows how fundamental research can spark these unexpected practical advancements.
Yeah, it really highlights that even areas we think are, settled in computer science still have room for breakthroughs.
Definitely.
So it sounds like both the Tiny Pointers paper and Krapivin's work are pushing the envelope on efficient data handling. And that's crucial for us developers trying to build performant, resource-friendly apps. Okay, so let's start with the core idea, tiny pointers. How do they actually work? What's the catch?
So the central concept is pretty straightforward. Represent references using fewer bits than normal pointers. Simple goal.
Okay.
But, as you guessed, there's a trade-off. It's not free.
Ah, the classic trade-off.
Right. When you actually follow one of these tiny pointers to get your data, there's a constant factor time overhead. So it might take a tiny bit longer.
Okay, a performance hit. How
Right.
much?
Constant factor. So not dependent on the size of your data, which is good.
Mm-hmm.
And the other part of the trade-off is a small, usually very small, probability of failure.
Failure, like it doesn't find the data.
Yeah, like the lookup might fail,
Mm-hmm.
and you might need a mechanism to handle that, maybe retry or fall back to a different method. Think of it like using a clever shortcut, usually faster, saves effort, but occasionally maybe you hit a dead end and have to backtrack.
Okay, a trade-off. Fewer bits for potentially a little more time and a tiny chance of a hiccup. That seems potentially worth it in many cases.
It often is, especially when memory is really tight.
So how small can these tiny pointers actually get? Is there like a formula?
Yeah, the paper gets into the theory of optimal sizes. It depends heavily on the load factor of the array or structure where your data lives,
Load factor. Okay, remind me.
just how full it is. So if we say the load factor is 1 delta, then delta represents the fraction of empty space.
Mm-hmm.
High delta, lots of empty slots. Low delta, it's pretty packed.
Got it. Like how full your hash table is, for example.
Exactly. And the optimal pointer size depends on whether you use fixed size tiny pointers, where all pointers have the same small size, or variable size ones.
Variable size, meaning some can be bigger than others.
Yeah, the average size is small, but some individual pointers might need a few more bits than others.
Okay, so fixed versus variable. What are the optimal sizes for each? What does that look like in terms of bits?
Okay, so for fixed-size tiny pointers, the paper shows the optimal size is theta log n plus log bits.
Whoa, okay, log in. That sounds tiny.
It grows incredibly slowly, like unimaginably slowly. For any practical data set size n, even astronomical sizes, log is a very small number, like 3 or 4 or 5.
Right, so that part is almost constant in practice.
Pretty much. The more significant part is often the log delta 1 term. Remember, delta is the fraction of empty space. So delta 1 is basically how many total slots you have per item.
Ah, so if the structure is mostly empty, you need fewer bits.
Exactly. If it's very densely packed, low delta, close to 1, you need more bits, which makes intuitive sense.
Okay, that's a huge potential reduction from the standard log dens, especially that triple log factor. What about the variable size ones?
For variable size, it gets even better on average. The expected optimal size drops down to just theta log delta.
Wow, so you lose the triple log term entirely on average.
Yeah, on average. Some pointers might need more bits, maybe up to the fixed size bound, but most will be very small, just related to the emptiness factor.
That dependency on the load factor, the delta, seems really key for developers then.
Absolutely.
Because if you're designing a system and you have a rough idea of how full your data structures will typically be, you can use these ideas to estimate the space savings.
Exactly. You can make an informed choice. Are the memory savings worth the constant factor time overhead and that tiny failure probability? It lets you tune the trade-off.
Right. Okay, so we've got the basic idea, the trade-offs, and the theoretical sizes. Now let's talk applications. Where can we actually use these tiny pointers in our code? The paper mentions several classic data structures.
Yeah, it highlights 5 key areas that are pretty relevant for developers.
Okay, let's hear them.
First up, just plain old space-efficient storage of key value pairs. Super common task.
Yep, use those everywhere. Hash maps, dictionaries.
Right. Suppose you need to store, say, n values, and each value takes v bits. You associate them with keys. Normally, the pointers or references themselves add significant overhead, especially if n is large.
Definitely. If you have billions of keys, the pointers alone could be gigabytes.
So the paper shows that with tiny pointers, you can still get constant factor time for lookups, insertions, deletions, the usual stuff.
Constant time, okay. And the space?
The total space becomes NV for the values themselves, plus only bits of overhead for any constant array.
What's that?
That's the iterated logarithm, like log star or log,
Wow.
so on. Basically, it grows even slower than log n. It's practically constant for all conceivable inputs.
So essentially NV plus almost linear overhead, but with a tiny factor.
Exactly. And here's the kicker for developers.
Mm-hmm.
To achieve this, you only need to store a tiny pointer with each key, and the expected size of that tiny pointer.
Let me guess. Related to delta.
Even better, expected size is bits.
Wait, constant expected bits per pointer. Seriously.
On average.
Okay, that's a game changer.
Yeah.
If you're building like huge in-memory caches or databases or just managing large collections of objects in your application, reducing pointer overhead to 0.1 on average, that's massive.
It really is. You trade that small potential slowdown and failure chance for potentially enormous memory savings. Makes things feasible that weren't before.
Wow. Okay, that's application 1. Super useful. What's next?
Application 2, making binary search trees succinct.
Succinct, meaning using basically the absolute minimum possible space.
Pretty much aiming for space usage, that's just 1 plus 0.1 times the theoretical minimum needed to just represent the data itself, plus maybe pointers.
So squeezing out almost every last bit of overhead?
Exactly. And the paper shows you can take any binary search tree and make it succinct using tiny pointers.
Any tree, like even balanced trees, AVL, red, black.
Yep. And you still keep the time for operation search, insert, delete within a constant factor of what they were originally.
Okay, so space becomes nearly optimal, time stays roughly the same factor. That's already good.
But they go further. They show it's possible to get down to bits of optimal space, like information theoretically optimal with modification times of only...
Log star time, the iterated log again. That's practically constant time.
For all practical purposes, yes. And this even applies to rotation-based trees, like splay trees and red-black trees.
That's incredible. So for developers using tree structures for searching, sorting, indexing,
Right.
especially if memory is tight, like in embedded systems or huge scalable indexes, this offers near optimal space with barely any time penalty.
Precisely. It's a very powerful theoretical result with practical implications.
Okay, 2 down. Key value stores, succinct trees. What's number 3?
Number 3 is about stable fixed capacity key value dictionaries.
Stable. What does stable mean here?
Stable means that once you insert an item, a key value pair, into the dictionary, its location in memory doesn't change, ever, even if the dictionary internally reorganizes or other items are added or removed.
Huh. Usually like in a hash table, if it resizes, everything might move, right?
Exactly. Rehashing shuffles things around.
So why would stability be important? Why keep things in the same spot?
It can be really important if other parts of your system hold direct memory addresses or pointers into that dictionary. If items move, those external pointers become invalid, leading to dangling pointers, crashes, data corruption.
Mhm.
It's messy.
Ah, I see. If you have external references depending on stable addresses within the data structure.
Right. So the paper shows you can use tiny pointers to build these stable dictionaries. You still get constant factor time overhead for operations, and the space overhead is minimal, like a 1 plus 1 factor again.
So you get the speed of a dictionary, but with the guarantee that your data stays put once inserted. And tiny cleaners make it space efficient. Neat. Okay, what's number 4?
Number 4 tackles dictionaries where the values can be of arbitrary sizes.
Ah, right. Many dictionary implementations are optimized, assuming values are all roughly the same size, like maybe just storing pointers to values elsewhere.
Exactly. Or assuming fixed size values stored directly. Handling truly variable size values efficiently within the dictionary itself can be tricky.
So how do tiny pointers help here?
They show how you can adapt a dictionary designed for uniform size values to handle arbitrary size values. You still get constant factor time overhead.
And the space cost.
The extra space cost per value is small. It's about log j for a value that itself is bits long. Again, that iterated log is tiny. The main cost relates logarithmically to the size of the value itself.
That sounds incredibly useful. Real-world data is messy. Values aren't always uniform size. Being able to stuff different sized blobs into a dictionary without killing performance or wasting tons of space, that's great flexibility for developers.
Definitely. It makes dictionary-like structures more versatile.
Okay, one more application left.
Yep. The 5th one deals with external memory arrays. This is for when your data is too big for RAM and lives mainly on disk.
Okay, the really big data sets.
Imagine you have a huge array on disk, maybe size 1 plus for epsilon, to store dynamic key value pairs. So you have a little extra slack space, controlled by var epsilon.
Right, some empty slots in the disk array.
The paper shows that using tiny pointers, you can maintain a small data structure in internal memory, just RAM, that acts as an index or stash.
How small is this in-memory stash?
Its size is only on log 1 bits, so it depends on how much slack space you have on disk. If you have reasonable slack, this can be much smaller than the main data set.
Okay, so a compact index in RAM, what does it let you do?
Here's the cool part. Using the stash, you can figure out the exact location of any key value pair in that huge external memory array in constant time.
Constant time lookup.
And crucially, with no disk I/O operations needed for the lookup itself.
Wow. No IOs to find where the data is. That's huge for performance when dealing with disk-based data.
It really is. You still need an I/O to fetch the actual data once you know where it is, of course. But finding its location becomes super fast, purely in memory.
So tiny pointers effectively help build a super fast, space-efficient in-memory index for massive on-disk arrays. That avoids tons of slow disk seeks just to locate stuff.
Exactly. It highlights how these techniques can bridge the gap between internal and external memory performance for certain tasks.
So looking back at these 5 applications, key value stores, succinct trees, stable dictionaries, variable size values, external memory indexes, it really covers a lot of ground.
It does.
The common theme seems to be use tiny pointers, get significant memory savings, often near optimal space, while keeping the time overhead to a small constant factor or even less, like log star.
That's the core value proposition, yes. It's a powerful tool set for developers focused on efficiency and scale.
It also sounds like developing these tiny pointer techniques wasn't trivial. You mentioned balls and bins.
Yeah, that's right. The paper mentions that getting these results required revisiting some classic problems in probability, specifically around how items, balls, distribute into locations, bins. They developed some new theoretical results there too, which might be interesting for folks more into the theory side of algorithms.
It's always cool to see how progress in one area, like probability theory, can unlock advancements in another, like practical data structures.
Definitely.
Okay, now let's loop back to Krapivin and his hash table breakthrough. You said it wasn't directly using this tiny pointers paper, but maybe related ideas.
Right. It seems his work was independent but explored similar themes of let's say, non-standard addressing or compact representation to achieve efficiency.
Yeah.
His focus was on designing a hash table that specifically avoided the standard uniform probing approach for handling collisions.
Uniform probing, like linear probing, quadratic probing, where you have a fixed sequence of places to check.
Exactly. He came up with a different way, and the result was pretty significant.
What was the specific result that turned heads?
He developed a hash table working with Farage Colton and Kurzweil, who helped formalize and prove it that achieves worst-case query and insertion times proportional to
Okay, and what's X there?
X is related to how full the table is.
Yeah.
Specifically, if D is the fraction of empty slots, then X1D. So, as the table gets fuller, D gets smaller, X gets bigger.
Right, so worst case time, how does that compare? Usually simple hash tables can degrade to linear time in the worst case.
They can, especially with bad hash functions or clustering.
Yeah.
But what made this result so interesting was that it contradicted a famous 40-year-old conjecture by Andrew Yao.
Yao again. What did his conjecture say?
Yao conjectured back in 1981 that for hash tables using uniform probing, the standard approach Krapivin avoided, the worst-case time for operations should have a lower bound of omega x, so linear in how full the table is, essentially.
So Yao predicted a linear lower bound, and Krapivin achieved polylogarithmic by not using uniform probing.
Precisely. And furthermore, Krapivin, Ferris-Colton, and Kurzweil actually showed that isn't just better than Yao's prediction for that model, it's actually the optimal bound for the class of hash tables Yao was originally considering.
Wow. So an undergraduate's exploration led to disproving a decades-old conjecture and finding the actual optimal bound. That's incredible.
It's a fantastic story. A real breakthrough in a fundamental data structure coming from thinking differently about addressing and collisions.
And it resonates with the tiny pointers theme. Even if not directly connected, this idea of finding clever, space-efficient, or computationally efficient ways to manage where data lives and how to find it.
Exactly. Even if Krapivin's specific hash table isn't immediately replacing standard libraries tomorrow, the underlying principle that challenging assumptions about addressing can lead to better performance is super relevant.
Yeah, it makes you think. Okay, so let's try and wrap this up. We've dived deep into tiny pointers. The big idea. Use way fewer bits for pointers.
Right. Huge potential memory savings.
With the trade-off being a small constant factor time overhead and a tiny failure probability.
Mm-hmm.
And we saw really practical applications for developers. Better key value stores, near optimal space for binary search trees with minimal time cost, stable dictionaries, handling variable size data easily, and even speeding up access to massive external memory datasets.
A whole suite of tools enabled by this one core idea.
And then we touched on Krapivin's surprising hash table result. Not directly tiny pointers, but showing how fresh thinking about addressing and data layout can break through long-standing perceived limits.
Yeah, challenging assumptions, finding new efficiencies. It's how the field moves forward.
So for you listening, especially if you're a software developer, this is all about building more efficient, more scalable systems.
Right, whether you're fighting memory limits, trying to shave milliseconds off access times, or designing systems for truly enormous data. These concepts offer new angles.
Which leads us to a final thought for you. How might these principles, using super compact pointers, or maybe the non-standard addressing approach hinted at by Krapivin's work, how might they inspire you?
Could they help you design a new data structure for your specific problem? Or maybe optimize an existing one in your code base, especially if you're dealing with resource constraints or just massive scale?
It's a great example of how theoretical computer science research, like the Tiny Pointers paper, can eventually filter down and give us practical tools and new ways to think about building software.
Absolutely. If you want to dig deeper, the Tiny Pointers paper is in ACM Transactions on Algorithms. And Krapivin's hash table work has been covered in various tech articles and blogs if you search for it.
Definitely worth exploring if this sparked your interest.
And we'd love to hear your thoughts. Can you see uses for tiny pointers? Or maybe Krapivin's ideas? Let us know.
Thanks for joining us for this deep dive. We'll catch